Hi, and welcome to the 3DOptimizer introduction video. In this video, I'm going to explain what 3DOptimizer is, what it does, and what it doesn't do. 3DOptimizer is a tool for finding a machine and material specific set of printing parameters such as processing temperature and printing speed, which are the most optimal for a certain machine and material combination. 3DOptimizer does not help finding geometry-specific parameters such as infill density and shape, parameter count, etc. 3DOptimizer could be used when you, for example, purchase a new spool of material and don't know quite yet at what temperature your printer will print it best, what is the best retraction distance, and how well it will bridge. The way 3DOptimizer works is that it generates test G-codes, provides some guidance for test value selection, validation, and testing order. To start using Optimizer, you will need to create an account, but since I have already done that, I will proceed to log in. In order to start our testing session, we need to create a new material object and a 3D printer object or a machine. I'll start with the material by going to Resources, Materials, and I'll press New Material there. I'll type in white ABS and leave its diameter to 1.75 millimeters. Now I'll create a 3D printer object by going to Resources, Machines, and pressing New Machine. On top, there's a list of most popular 3D printer presets. However, for the sake of this video, I'm going to create my own 3D printer definition. I'll name my 3D printer my printer. I'm going to set its size to 200 millimeters by 200 millimeters, which in this case is also the diameter of my print volume, since my printer is a delta printer, which is the same as circular or elliptic printer. My printer has a Bowden type extruder. It supports temperatures of up to 300 degrees Celsius, has part cooling, and it has a 0.4 millimeter nozzle. My printer does not have a heatable chamber, but it does have a heated print bed, and it can be heated to 120 degrees Celsius. Now I'll press Submit. For most printers, you can find the necessary parameters in the printer's product sheet. It is also very important that the printer is well calibrated and leveled before testing. So now that we have created material and machine definitions, we can go ahead and create a new session. I'll name the session Tutorial Session. I'll select our newly created material and machine. The optimization strategy field will bias the testing process towards one of these qualities. If you wish to achieve good-looking parts with no regard for the mechanical strength or printing speed, you might want to select Aesthetics. This will cause Optimizer to suggest lower temperatures, lower track height, and slower speeds. For mechanical strength, it might suggest higher temperatures, slower speeds, in order to maximize layer adhesion. As for short printing time, Optimizer would suggest thicker layers, greater feed rates, and higher temperatures. At the end of the day, it is up to you to use these suggested values or not. Now that we have selected all the values, we can click Initialize Session. What we're seeing now is the test generator view. From here we can switch between tests and we can fill in all the values relevant for this test. On the left there's a list of all available tests. The ones in the bold text are core tests and those who have the biggest impact on the final result. In most cases it is only necessary to go through these tests. The top two rows there are the most significant, as they are showing what parameter combinations are going to be used in the matrix. Currently, we can see that 7 first layer track height and 4 printing speed values are going to be tested, making it a total of 28 different combinations. We can change the border values to change what values will be used throughout the test, but I am happy with the suggested ones, so I'm not going to do that. There are some values that need to be specified before we can actually print anything. These values will most likely be provided by the materials manufacturer either on the filament box or the spool itself. In my case, it says that the print bed should be 90 degrees Celsius and the first layer extrusion temperature 250 degrees Celsius. I'm gonna type those in and proceed to the validation step. In validation step, I can download the test G-code, print it, and evaluate the results. This chart represents the test structure as it is printed on the print bed. The wipe strip is on the bottom, the lowest value is on the right, and the speed increases from the top to bottom. I will select the second tile from the top and second from the right side, and I'll press submit. Notice that I am now redirected to the third test and not the second one, which is the first layer track width test. That's because since I printed with 0.4mm track width and found a valid test structure, there is no real reason to change it. If I had found gaps between tracks or just had not found any good tiles to choose from, I would need to do that test as well. So now we are going to test parameters that affect all layers above the first one, starting with arguably with the most important parameters, extrusion temperature and printing speed. I am going to leave the suggested values for extrusion temperature, but I am going to change the printing speed to something much higher, 30 to 70 millimeters per second, as suggested right here. I also need to select the track height value before I can actually generate the G-code. I'm going to select 0.15 millimeters, which is a good general purpose height for a 0.4 millimeter nozzle. It is possible to test different track height values in a later test if necessary. I'll press submit now and proceed to download and print the generated G-code. I'll select the best tile in the validation matrix and I'll press submit. As you can see, we have jumped over 6 tests. Again, that is because if we manage to find the ideal settings in the third test, there is no real need to do the following 6 tests. However, if the surface of the printed tiles is coarse, with gaps between tracks, with interruptions or other defects, the optional tests may help improve the print quality. You can find more information about what each test is intended for by clicking on the test and having a look at their description. For my purposes, I am satisfied with the result achieved in the previous test, so I'm going to proceed with the retraction distance test. In this test, in addition to the retraction distance interval, we can also change retraction speed. I will not change the retraction distance interval and I will not change the offered retraction speed. Note that the retraction distance and speed can be fine-tuned in the next test. I'll proceed to download and print the G-code file. As you can see, the validation matrix now has a single row, just as the test structure. So this is the finished test structure. As you can see, the bottom is here where the wipe strip is. So the values go from right to left, this being 0 and this 6 millimeters of retraction distance. And as we can see, improvements really start to show at 3 millimeters of retraction distance, and it doesn't really improve from there. So this is the value we're going to pick. This is 3 millimeters of retraction distance. I will select 3 millimeter retraction length and press submit. We now have reached the last test in the testing session. In this test we'll look for optimal bridging settings. Bridging performance is mostly affected by bridging extrusion multiplier, by bridging speed and cooling. We will leave the bridging extrusion multiplier as it is. In most cases, extrusion multiplier needs to be increased for optimal bridging. Bridging speed, however, is less predictable as it can be sometimes faster, sometimes slower than the printing speed. I will go for lower bridging speeds and select the suggested interval of 15 to 35 millimeters per second. Part cooling while bridging needs to be on more often than not, so I will set it to an arbitrary number like 50% and I'll proceed to generate and print the G-code. So this is the bridging test structure. as you can already see, it is quite a bit different than the previous ones. And the reason that is that it prints in a triangle and then draws a bridge to the other side of that triangle. So you can also see different lengths, how it will bridge with different lengths. And as you can see, like these are the test tiles, these triangles right here. So this one would be considered the slowest speed and the lowest extrusion multiplier value. Right here, this one would be slowest speed, highest extrusion multiplier value, and this would be the highest speed and the lowest extrusion multiplier. And so we can already see that the bottom rows are quite unusable. The second row maybe already starts getting useful, these two structures right here, tiles rather, sorry. And the bottom, or the slowest row I should say, is already quite good. Like this bridging right here is as good as it comes. And what we're looking for is even spacing of the tracks and good weld together. You can see some gaps between these tracks here. This is also workable, but you can see that there are no gaps here. So this is the best structure. Tile, sorry. I will select the upper middle tile and press submit. I'm now redirected to the overview page where I can see all the tested and selected values. On the bottom of the page I can download a configuration file which will include the selected values and some values derived from the optimization strategy. Please take into consideration that these configuration files will not work universally for all geometries and are somewhat general. You'll still need to change geometry specific parameters, but all the material machine specific parameters from Optimizer will be there. At the time of making this video, Cura Profile Generator is still highly experimental and will not work for everyone. If that's the case, you can still enter the selected values manually from the session overview. This concludes our basic session walkthrough. Thank you for watching, and we'll see you next time.